Hi, this video we're going to explore how to solve word problems using exponential functions. So an exponential function is usually called an exponential growth function if the function is increasing, or it's called an exponential decay function if it happens to be a decreasing function. So let's look at our first example. So the example says the function n of t is equal to 5,723 times 1.33 raised to the t, models the number of Netflix subscriptions in thousands at the beginning of each year from 2007 to 2015, where t equals 0 corresponds to the beginning of 2007. If the growth continues to be modeled by this equation, predict the number of subscriptions at the beginning of the year 2020. So we have to figure out what we're going to plug in for t into our function to compute the number of subscriptions at the beginning of the year 2020. So we have to figure out how many years have elapsed. So if the year 2000 is t equals 0, then the year 2020 is t equals 13 because 2007 plus 13 years will get us to the year 2020. So we have to add 13 years to the initial time. All right, so that means we're going to plug in 13 for the variable t in the function. So the number of subscriptions in the year 2020 is going to be n of 13, which is 5,023 times 1.33 raised to the 13. So now we're going to use our calculator. So when you do these problems using a calculator, you shouldn't do any rounding until the very end of the problem. So in other words, don't compute a number on your calculator and then write down a number and then start multiplying. Leave as much in your calculator as possible and do all the computations on the calculator and only write down your final answer. Because when you write down an answer, you're going to have to chop off that decimal someplace, and that's called rounding. So we just want to chop off a decimal once at the very end of the problem. So what you do is you put in 1.33 and then you raise that number to the power 13 using the exponent key on your calculator. And then you get a long decimal, but don't write that number down, just leave it on your calculator. And then hit the multiplication button and then the 5,723, and you get another long decimal. And then that's the one that you'll chop off. So when I do that, I get 23,318 point, and then I just chopped it off after 4 decimal places, so I got 0.0298. But I have to remember that in this problem, these numbers are in thousands. So this is really times 1,000. So I'm going to multiply that number by 1,000 to actually see how many subscriptions we have. So when I multiply the long number by 1,000, I'm moving the decimal place 3 places to the right to make it a bigger number. And I get 23,318,029.8. And now I have to remind myself that in this problem, this number represents the number of Netflix subscriptions. Is it possible, does it make sense to have 8/10 of a Netflix subscription? I think not. So we definitely need to round to the nearest whole number, just because it doesn't make sense to have a decimal in this situation. So we're going to round it up to, instead of 29.8, it's going to be 30. So it's going to be 23,318,030 Netflix subscriptions. Okay, so that one was clearly an exponential growth problem. That is a function that was increasing. Okay, great. Let's look at the next one. Number 5. So number 5 says that the rate of inflation is 3.7% per year, and the future price in dollars of a certain item can be modeled by the exponential function P of t equals 1500 times 1.037 raised to the t, where t is the number of years from today. So this is clearly an exponential growth problem as well. Inflation means prices are going up, and this function is getting bigger. As t gets bigger, all those numbers get bigger. So we're asked to find, in part A, the current price of the item. So we know we have a function that'll tell us the future price, t years from today, but we want to know what is the price of the item today. Well, today, so the future price is t years from today, but the current price means that t has to be 0. 0 years from today would be today. So let's plug in t equals 0, and we get p of 0 is 1500 times 1.037 raised to the 0. And 1.037 to the 0 is 1, so we get 1500. So the current price of this item has to be $1,500. Okay, let's look at part B. Part B says, how much will the item cost 9 years from now? And now we're asked to round our answer to the nearest dollar. So 9 years from now means that t is going to be equal to 9, so we can plug in p of 9. So p of 9 will be 1500 times 1.037 to the 9. So once again, just put in your calculator 1.037, raise it to the 9th power, to the exponent 9, leave that number in your calculator and just hit times 1500. And you'll get a decimal, but you want to round it to the nearest whole number. So you should get 2080. And that means that the current price is $2,080. There we go. All right. Let's move on. Number 6. So number 6 says, in 2005, a principal of $2,300 was invested at 3.75% interest, compounded annually. Let t be the number of years since 2005, and let y be the value of the investment in dollars. So we're asked to write an exponential function showing the relationship between y and t. So we have to come up with the function. That's all we have to do in this problem. So let's look for a pattern and see if we can write down an equation that sort of summarizes the pattern that we found. So first of all, we're told that the initial investment was $2,300. So in 2005, when t is equal to 0, so 0 years since 2005, we know that y is equal to 2,300. So then let's see what happens a year later. So in 2006, that's 1 year after the year 2005, what is this investment going to be worth? Well, it's going to be the previous year's amount plus 3.75% of that previous year's amount, okay? Because it's interest on the previous year that's being added to the previous year. Okay, so we start with the previous year's amount, and then we add the interest on that amount to get the next year's amount. So the previous year's amount was $2,300, as we saw, and so we're going to add 3.75% of 2,300. So it's 2,300 plus 2,300 times 0.0375. Now, I can go ahead and compute that, but we're looking for a pattern. So it's best not to actually put this in our calculator, but to see if we can write it in a compact way and leave it in that compact form and then do it again for the next year. See if we can find a pattern. So what I'm going to do is I notice I have two terms being added together. 2,300 plus 2,300 times some number. So what I'm going to do is factor 2,300 out of both of those terms. So that's my GCF, right? So I can pull out a 2,300, and then in the first term I'm left with 1, and the second term I'm left with that 0.0375. So I can add 1 plus 0.0375. So I get 2,300 times 1.0375. So that's in the year 2006. Now I'm not going to multiply that out because remember, I'm looking for a pattern. So let's see what happens a year after that, in 2007. So 2007 is 2 years after 2005. So now we're going to take the previous year's amount and add the interest to it to get the new amount. So we're taking previous amount, we're adding 3.75% of that previous amount to get the year 2007 amount. So what's the previous amount? Well, that was the 2006 amount. So I'm going to write 2,300 times 1.0375, that's the previous amount, plus another 3.75% of that. Well, we saw in the previous year how to do that. What we're going to do is just multiply by 1.0375 because that was the trick that I did in the last one. I just factored out the previous amount and I was left with a 1 plus 0.0375. So I'm just sort of skipping that step and writing the result. So I look at this and I go, oh, okay, so I have 2,300 times 1.0375 times another 1.0375. So I can rewrite that as 2,300 times 1.0375 squared. So that's interesting. So when t equals 1, I got 2,300 times 1.0375 to the 1. And when t equals 2, I got 2,300 times 1.0375 to the 2. Let's see what happens when t equals 3. So in 2008, when t equals 3, y is going to be the previous amount, which is 2,300 times 1.0375 squared, times another 1.0375. So we can see that in the year 2008, when t is equal to 3, y is going to be 2,300 times 1.0375 to the 3. So we see a pattern. Each year, we just multiply the previous year's amount by another 1.0375. So now we can write down a nice compact function that'll give us the investment amount, the value of the investment in any year t, any t years after 2005. So I can write the function relating y and t is the following. It's going to be y equals 2300 times 1.0375 raised to the t. So that, again, is another exponential growth function. All right, let's look at number 7. So number 7 is about the rats at Fisherman's Wharf in San Francisco. So this one says, assume that the rat population of Fisherman's Wharf grows at a rate of 8% monthly. If there are currently 200 rats at Fisherman's Wharf, that word in is not supposed to be there. So if there's currently 200 rats at Fisherman's Wharf, find an exponential function that models the rat population t months from now. So let me show you what we've been doing. So an exponential growth function, which is what we've had so far on this worksheet, and what we have right here, the rat population, always has a certain form, and an exponential decay function has a very similar form. So both of these are going to be, we're going to use y of t is going to be an amount y of 0, which is called the initial amount, times 1 plus that percent of the growth rate, or that percent that we're given, raised to the t. That's the exponential growth function. And an exponential decay function is similar. It's the initial amount times 1 minus the rate, or the rate of decay, raised to the t. So, as I said, y of 0 is the initial amount. So it could be initial population, like with the rat population, or an initial investment, like in the last example. Okay, so let's use this for this problem. So the rat population, it says it's growing at a rate of 8% monthly. So that means that our rate is going to be 0.08. And we're told that the current rat population is 200 rats. So that's our initial amount, or initial population. And I'm going to use P for population. So let's let P of t be the rat population t months from right now. So we're going to write down the exponential growth function that represents the rat population at Fisherman's Wharf. So the initial population was 200 rats, so that's P of 0. And P of t, the population t months from now, is going to be the initial population, 200 rats, times 1 plus the rate of growth, 0.08, raised to the t. Now let's add the 1 plus 0.08, so we get 200 times 1.08 raised to the t. And that's the exponential growth function that represents the rat population. So let's look and see what part B asked us to do. So part B says, use your function in part A to predict the rat population at Fisherman's Wharf in 2 years. So 2 years, how many months is that from today? 2 years is going to be 24 months from today. So that means we can plug in 24. So P of 24 is 200 rats times 1.08 to the 24. So we put in the calculator 1.08, raise it to the exponent 24, and leave that number in your calculator and just multiply it by 200. And we get some decimal. I chopped it off after 3 decimal places. But we have to now round it because we're talking about rats, right? This is the number of rats. And it doesn't make sense to have 0.236 rats. So we have to chop it off at the nearest whole number. So I'm going to round it to 1,268. So there will be about 1,268 rats at Fisherman's Wharf 2 years from now. All right, so those are examples of exponential growth problems. We didn't actually do an exponential decay, but just remember, if it's a decay, you're going to subtract the rate, the exponential decay rate, r. It's going to be 1 minus r instead of 1 plus r raised to the t. Okay.